Okay, this is a part one video that covers an old PowerPoint presentation that I did way back when. This was supposed to be a coverage of information theory for a layman type of audience. In fact, I gave it to a group of professors from the humanities. All right, so I'm going to add a few more details, technical details that I know you guys can handle, but it does give you a picture of Claude Shannon's information theory. Now, you should also know I'm a big fan of Claude Shannon. I think he's one of the giants of our time. He came up with this idea of information theory, and honestly, without some of the ideas that he imparted into this process of converting signals into bits, without his insights, we wouldn't have the communication structures and systems that we have today. So information theory can be broken up into two main categories: source coding and channel coding. We're going to start with source coding first, and in part one, really, we're just going to introduce you to the problem that needed to be solved. Okay, so let's move on a little bit. Okay, so the idea here is that we have information, and in the communications context, I grabbed a bunch of pictures here. I'm thinking of music and pictures and video and art and things that we want to capture in some type of medium. We need to be able to represent that in bits, so that number one, we can put it on things like computers, and then number two, we can send that information to where we want to send it. So we already know about this. We know that we capture all kinds of things and turn those into bits. All right. So what do we do with those bits, and how do we manage that, and how do we represent things? That's the subject of source coding. Okay. All right. So how'd you like that transition? So I told you this is a really old presentation. I'm going to do that again so you can watch it. Okay, so as I make this slide transition, this makes a conversion into the old movie, The Matrix. I just noticed that it was 20-ish years old recently. And so back in the days, that was kind of a big deal. You remember the idea on that was, is the world real or is it virtual? So that's one of the ideas that comes from The Matrix. Anyway, I wanted to throw that in there. So it turns out information theory is, there's no argument really, it's the mathematical foundation of this digital revolution that we've had in terms of communications and cell phones and all the things that we know about. Okay, so let's talk about some of that. Before we move on, I also wanted to point out, this is my copy. I took a picture of myself holding my copy of the book called The Mathematical Theory of Communication, Claude Shannon and Warren Weaver. I don't know much about Warren Weaver, but Claude Shannon, it was his ideas. He published these ideas in a pretty short little book, and it's surprisingly readable. All right, you would think this giant in our field, he's come up with these ideas. He was able to distill those down in a pretty simple form and give some examples that are pretty easy to relate to. So, I love these ideas. I felt like, geez, I need to have this book sitting on my shelf in my home office. And in fact, I wanted to prove to you that I do, in fact, have that book. So recommend that. You can get it off the internet for like $15. It's a good thing to add to your collection. Okay, so in this presentation, we're going to go three things. I wanted you to know the significance of information theory and how it's useful for communication problems. And then once you know about the significance, we're going to get into the details of how do you measure information, what's the intuition that Shannon had, the insight that he had that allows us to come up with some measurement of information that we can use to come up with source coding ideas and later on channel coding ideas. All right. And then in the second video, we're also going to do some examples that cover some of these things with calculations. And my philosophy is if you can't do some calculations, you don't really understand it. So hopefully we'll do enough of those calculations where it seems real for you. Okay, so the title of this slide, What Hath God Wrought? Okay, very interesting background on that message. Number is 2323. So it turns out the first telegraph line between Baltimore and DC, it's about a 20-mile loop, right? That's, allegedly, or urban legend, or maybe it's even true, is that that's the first Morse code message that was sent between those two cities with that communication link. Okay, so interesting enough. I bring up Morse code because later on we're going to be able to relate some ideas behind information theory back to Morse code. And you've probably heard of Morse code. I'm not sure how much you know about it. I don't know a lot about it, but I know it's essentially dots and dashes and pauses so that you can communicate over, in really a digital fashion. There's a code that you use to represent text. That came along before we had regular phone lines. Okay, so to place all this work that Shannon did into context, we were just coming along in the 40s and 50s looking at switching devices. We knew about the vacuum tube, we were developing the transistor, and because things could switch, it generated an interest in things that are digital, representing things as either on or off. Vacuum tubes can do that, transistors, obviously, we still use those for that. Okay, Claude Shannon and Nyquist, I can't remember Nyquist's first name. He was also, Nyquist was also a person that worked at Bell Labs, and Bell Labs, remember, the phone system at one point was nationalized. You didn't have, private phone companies. It was just a national phone service. And so both these guys worked at Bell Labs, where they did a lot of high-level research in terms of, information and communications and how to represent those things. Okay, so Nyquist came up with sampling theory with the idea of how do you represent analog signals with bit sequences, and of course we've talked about that a lot in this course. All right, so that's the context. And so then when you start talking about using bits to represent analog signals, you start looking at the idea of bandwidth. All right, and so remember, this presentation was originally for a layman audience. The equalizer, you think of the equalizer as, knobs that you turn on your stereo to boost the treble or boost the bass or what have you. You already know, because you're electrical engineers, you know about bandwidth. All right, so it turns out if you wanted to make a phone call, we know that the frequency content of speech can be filtered down to about 4 kilohertz, and it still sounds decent. All right, it sounds like a phone call, basically. All right, so old-fashioned phone calls used about 4 kilohertz of bandwidth. Okay, at that point in time, if we decided, we're going to digitize speech and send it over the same channel, all right, well then the calculations would go, if I have 4 kilohertz of bandwidth that represents the speech signal, I need to sample that at least 8,000 samples per second. All right, so you know that. And then each sample would take at least 8 bits. If you go much below 8 bits, you don't have enough levels and it doesn't sound very good. Okay, so 8 bits. So 8,000 times 8 is 64,000 bits per second. And then the technology of the day, it took between 1 and 2 hertz of bandwidth to represent a single bit. All right, so you can come up with this rule of thumb that if you wanted to digitize a phone call, you're now expanding the required bandwidth to 64 kilohertz. All right, so that to us today sounds like nothing, but we're not thinking about the switched phone system. The switched phone system, every channel had 4 kilohertz, and if we tried to expand that to 64 kilohertz per channel, that was a no-go. That was a showstopper, and it made the idea of going to digital seem impossible, I guess, maybe. I'd be interested in talking to people from those days to see what the, engineers from those days to see what the thought was. It just it maybe seemed like a pipe dream until Shannon comes along. Okay, another example of solving this bandwidth problem is, I found this in my old presentation. This is a Napster logo. I don't know if you remember Napster. It was a peer-to-peer sharing network, and a lot of people used it back in the day to essentially share music that was encoded with MP3. So the reason you encode something with MP3 rather than just taking the CD and ripping it to a WAV file is that the encoding of MP3 used some redundancy within speech to reduce that bit requirement. So you don't need nearly as many bits to represent, to a certain fidelity, the audio quality of the music. Okay, so the bandwidth problem was essentially solved by source coding, and this MP3 idea is an example of source coding. Okay, so that hopefully puts the context of information theory in place for you. The second part of this is going to talk about some of the detailed calculations that we use to represent information.